Hello everyone and welcome. In this video, we're diving into the world of graph algorithms, specifically focusing on the most frequently asked graph problems in coding interviews. Whether you're just starting your journey into data structures and algorithms, or you're brushing up on your skills, this video is designed to help you understand and tackle graph-related questions with confidence. Before we jump into specific algorithms, let's cover some graph basics. First, graphs are composed of vertices, also known as nodes, and edges which connect these vertices. Next, there are directed graphs where edges have a direction, indicating a one-way relationship, versus undirected graphs, where edges have no specific direction, showing a two-way relationship. Graphs can also be weighted, where each edge has a value, or unweighted, where all edges are considered to have the same weight. Finally, graphs can be represented in code using either an adjacency list, which lists the neighbors of each vertex, or an adjacency matrix, which is a two-dimensional array indicating whether there is an edge between any two vertices. Now let's explore how graphs are represented in code. On the left, we have an adjacency list represented using a Python dictionary. Each key in the dictionary represents a vertex, and the corresponding value is a list of its adjacent vertices. For example, vertex A is connected to vertices B and C. On the right, we have an adjacency matrix. A 1 in the matrix indicates an edge between two vertices, while a 0 indicates no edge. For instance, the entry at row A, column B is 1, showing that there is an edge from A to B. Similarly, the entry at row B, column A is also 1, indicating the edge from B to A. This is for an undirected graph. The choice of representation depends on the specific problem and the trade-offs between space and time complexity. Let's delve into breadth-first search, often abbreviated as BFS, a fundamental graph traversal algorithm. In BFS, you explore all the neighbors of a node before moving on to their neighbors. The code on the left shows how to implement BFS in Python using a queue. We start with a given node, add it to a queue, and mark it as visited. We then process each node in the queue by visiting its unvisited neighbors and adding them to the queue. On the right, we have a graph visualization showing the BFS traversal pattern. The nodes are numbered in the order they are visited. BFS is useful for finding the shortest path in unweighted graphs and performing level order traversal. Now let's explore depth-first search, also called DFS, another fundamental graph traversal algorithm. In depth-first search, we explore as far as possible along each branch before backtracking. The code on the left shows how to implement DFS recursively in Python. We start with a given node, mark it as visited, and then recursively visit each of its unvisited neighbors. On the right, we have a graph visualization showing the DFS traversal pattern. The nodes are numbered in the order they are visited. DFS is useful for finding connected components and detecting cycles in graphs. Let's learn about Dijkstra's algorithm, which is used to find the shortest path from a source node to all other nodes in a weighted graph. The code on the left shows an implementation of Dijkstra's algorithm in Python using a priority queue. We initialize the distances to all nodes as infinity, set the distance to the source node to 0, and add the source node to the priority queue. We then process nodes from the priority queue, updating the distances to their neighbors if a shorter path is found. On the right, we have a graph visualization, highlighting the shortest paths found from node A. Dijkstra's algorithm is a powerful tool for solving various optimization problems. One common graph problem is detecting cycles. The code on the left demonstrates a DFS-based approach to detect cycles in a directed graph. The hasCycle function uses a visited set to keep track of all visited nodes, and a recursion stack to keep track of the nodes in the current path. If we encounter a node in the current path that has already been visited, we have found a cycle. On the right, we have a graph visualization. The dotted line indicates a back edge, which creates a cycle. Being able to detect cycles is crucial in many applications, such as task scheduling and dependency resolution. Topological sort is an algorithm for ordering the nodes in a directed acyclic graph, also known as a DAG, in such a way that for every directed edge from node A to node B, node A appears before node B in the ordering. The code on the left shows an implementation of topological sort in Python using depth-first search. We perform a depth-first search on each node in the graph, adding nodes to a stack after visiting all of their descendants. We then reverse the stack to obtain the topological order. On the right, we have a graph visualization showing course prerequisites. Topological sort can be used to determine the order in which to take the courses. The union-find data structure, also known as disjoint set, is useful for tracking a set of elements partitioned into a number of disjoint, also non-overlapping subsets. The code on the left shows an implementation of union-find in Python. The find function determines which subset a particular element is in. This can be used for determining if two elements are in the same subset. The union function joins two subsets into a single subset. On the right, we have a visualization showing two disjoint sets. Union find has applications in detecting cycles in undirected graphs, finding minimum spanning trees, and solving network connectivity problems. A minimum spanning tree, also called MST, is a subset of the edges of a connected weighted graph that connects all the vertices together, without any cycles and with the minimum possible total edge weight. There are two popular algorithms for finding the minimum spanning tree: Kruskal's algorithm and Prim's algorithm. Kruskal's algorithm sorts all edges by weight and adds edges to the MST from smallest to largest, skipping edges that create cycles. Prim's algorithm starts from any vertex and adds the smallest edge connecting the MST to a non-MST vertex, repeating until all vertices are included. On the right, we have a graph visualization showing a minimum spanning tree, with the MST edges highlighted. A strongly connected component called SCC in a directed graph is a subset of vertices such that for every pair of vertices in the subset, there is a path from the first vertex to the second vertex and back. Kosaraju's algorithm is a popular algorithm for finding strongly connected components in directed graphs. The algorithm involves first performing a depth-first search and storing nodes in order of finishing time. Then transposing the graph and performing depth-first search on the transposed graph using the finish time order. Each depth-first search tree is a strongly connected component. On the right, we have a graph visualization showing two strongly connected components. To further enhance your understanding and skills in graph algorithms, here are some practice problems and learning resources that will be helpful. Some top interview problems include number of islands, clone graph, course schedule, word ladder, network delay time, and is graph bipartite. Some helpful learning resources include algorithm visualization tools, graph theory fundamentals course, competitive programming websites, graph problems analysis blog, and interview preparation guides. Mastering graph algorithms separates good programmers from great ones. Good luck and thank you! If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.